Welcome you to this series of lectures on marine hydrodynamics. In the last lecture, we have talked about boundary layer theory. Basically, our concentration was on the general two dimensional boundary layer equation derivation, and we have highlighted that the limitation of the boundary layer theory, particularly there is a class of flow problem for which boundary layer theory will not hold good. Today, we will discuss about the solution procedure for the boundary layer equations. Just before that, we have seen that the solution procedures are very few problems in viscous associated with viscous fluid flow has we can get exact solution or the closed form solutions. On the other hand, and that is basically for the unidirectional flows. On the other hand, when you look into the boundary layer equation, even if in the two dimensional boundary layer equation, it is not easy to get a closed form solution. The reason is that the presence of the nonlinearity in the convective terms, and that makes the problems more complex because there is a nonlinearity, and that so because of that we have to take the help of numerical methods. So, it is not that always all kinds of numerical methods we can apply. So, still we try to simplify the problem to reduce the number of variables or to bring the problem to the form of integral, which will be more easy to handle, or maybe sometimes directly we go for a numerical method like the finite difference one. Before going to discuss the various solution procedures and the limitations, let us see what are the various types of flow. Before we go into analyzing a particular flow problems, we need to, it is better to know what type of flow it is, and one has to check, because the moment one is clear about the type of nature of the flow, then it becomes much easy to handle a problem and use a appropriate method for its solution. So, let us see what are the checks one has to have before going to the solution procedure. Basically, one has to see that whether the flow is steady or unsteady. Flow is steady or unsteady. If it is unsteady, for unsteady flow, then whether the flow is a transient or oscillatory. Transient or oscillatory. Transient or oscillatory. Then again whether the flow is laminar or turbulent. Fluid is compressible or incompressible. Then again the fluid motion is Newtonian or non-Newtonian. And again if we are dealing with a flow which is a boundary layer, there the boundary layer theory is applicable, particularly the outer flow. In that case, the outer flow, that means the flow beyond the boundary layer is whether the outer flow is based on an Euler equation or a potential type. In fact, in some of the problems the outer flow nature is known, and again whether the outer flow nature is known or not. Outer flow is known completely. is known completely or to be determined. Because the moment all these characteristics are known, so because we all deal with the partial differential equations associated with it. So, all these characteristics will highlight, sometimes gives us the information whether the flow is an elliptic, the problem is an elliptic problem or a parabolic problem, because depending on the elliptic or parabolic nature of the problem, we can say that the whether it will lead to a boundary value problem or a initial value problem, initial boundary value problem. Even if sometimes, yeah, so this is the class of problems we will come across, and one has to go for a check before attempting any flow problem for attempting any problem for solution. Check for this, for the nature of flow. This check is a must, because that will simplify the procedure and also the time one spent for understanding the flow pattern. And then if you look into solution procedure, normally as I have mentioned that boundary layer equations, they are nonlinear equations and it is difficult to get a closed form solution, one has to take the help of the numerical methods. So, analytical solution is ruled out for boundary layer equation. Analytic solutions methods, analytic solution methods ruled out for boundary layer equations. However, what we can do, we can always apply the self similar solution, we can always get a self similar solution approach. As we have seen that in self similar solution approach, we have two things. Often we convert the partial differential equation to ordinary differential equation. This conversion helps to a great extent, because and also in some situations we reduce the number of variables, also it reduces the number of variables. So, basically what is similarity theory? Let us say similarity. What is similarity theory? Before going to know this similarity theory, the similarity theory tells us for two arbitrary sections, suppose we have two arbitrary sections in the fluid flow, have two sections, let the sections be arbitrary x1 and x2, then the principal variable must satisfy then they must satisfy, that means u x1 g x1 by u naught x1. U naught x1 is the outer flow, is same as u of x2 g of x2 divided by u naught x2. If this holds, and where what is that? Where g is what? Eta is equal to y by gx, and this is a non-dimensional variable. Rather non-dimensional, rather call it dimensionless variable. And what is gx? In fact, gx is of the nature, and here what is happening, this eta y by gx, and again this gx is proportional to the Reynolds number, to the local boundary layer thickness. often this Gx is proportional to the boundary layer thickness. And because of this variable, what will happen, this y by Gx, when you put eta and we convert this, because we have dealing with we have various components. The whole problem, by doing this, we can bring down the whole problem to a problem of that x and y variable. We can reduce to just a problem of a variable called eta, and we can recast the whole problem into from a two dimensional partial differential equation to a one dimensional to an ordinary differential equation. So, it is quite possible that many situations it is possible to convert a two dimensional PD to an OD. And this principle also will hold good when there is no singularity in the boundary layer flow, but with a specific u naught x which is known. And particularly u naught x is more suitable, this similarity approach is more suitable when u naught x is the solution associated with the corresponding potential flow problem beyond the boundary layer. Now, with this is the basic assumption on which the similarity method will be based on, and we will come to an example a little later. Before that, let us go to the what is the integral method. Unlike the case of a similarity transform similarity theory, where we are converting the problem to from a partial differential equation to ordinary differential equation, basically we are reducing the number of variables in the equation. In this case, this is another approximate method which is a special case. It is a special case similarity. This integral method, what we will call, it is called a special case of the method of residual, weighted residual. And what is the method of a weighted residual? Sometimes we call it MWR, method of weighted residual. And this method, suppose I have a linear operator, I have operator L phi, that is basically the boundary value problem. If L phi is 0 for an unknown function phi, L is the differential operator, then we are looking for a solution. Always what we can do, we can approximate phi by phi hat, phi we approximate by phi tilde, and then we say that if phi tilde is the approximate solution of this. So, it is obvious that because we are looking for phi tilde is approximate solution to phi, then it is obvious that L phi tilde will not be 0, because we are this is phi tilde is an approximate solution. But what will happen, L of phi tilde will be identical to R, and what is R? R is basically satisfy, the R satisfies, this is in a very simple form, R satisfy over the domain omega W R dr d omega is equal to 0, and this is what is called, and W is called the weight function. W is called the weight function. In fact, this is the method of weighted residual, and R is called the residual weight function, and R is the residual. R is called the residual. Then there are four such methods based on this weighted residual, and basically depending on the nature of W, particularly the weight function, we always the method of weighted residual changes. So, there are I will couple of methods are depending on this nature of W, that is the weight function. Basically the methods comes up, and then from this we call 4 methods basically integral method. The other method is called the collocation method. These are part of the, and then sometimes we call it Galerkin finite element method. Galerkin finite element method, and the other one is called controllable method. In fact, all these methods, this integral, this method of weighted residual is a very robust method, one of the robust method, and one of the advantage is that because particularly when we have corner points, we have flow singularity at the boundary. Well, basically while dealing with the boundary value problems and having flow singularity, this is a one of the robust method. And here this flow singularity, when I say in mathematical terminology, we may say that they have integral singularity. This will be obvious when we come to problems and see, and which is otherwise not possible by the standard finite difference method. It is very difficult to handle a singularity in the flow, even if the singularity is integrable in nature by the finite difference scheme, because convergence will be very slow by the finite difference scheme. On the other hand, this will be, and another advantage is that when you think of anything of integration, we go for a summation kind of things. So, error associated will be much less and easy to handle. So, almost all the boundary conditions or initial conditions can be always clubbed together with the integral in this method. That is one of the beauty of this integral methods, of the what we call the method of weighted residuals. So, with this understanding we will discuss, our emphasis will be on the integral method. And again, if before going to, there is another method which is used for the boundary layer equation, that is basically the finite difference method, and that is a direct method. I am not going to the details of this finite difference method. Most of you have a knowledge on this finite difference method. I am not going to the details of this. So, before going to, so these are the 3 methods which are, one is the method of similarity theory, the other is integral method, and the third one is finite difference method. So, with this I will emphasize basically in this, give examples to illustrate the role of similarity theory and integral method in solving boundary layer equations. Here, before going to solve a problem, let us define few terms. What is wall shear stress? I think while I have talked about viscous fluid, I have already told the wall shear stress tau W is defined at mu del u by del y at on the wall boundary y W, and sometimes we call it a local shear stress. If the wall is at 0, then we call it, sometimes we call the del W x is mu del u by del y at y is equal to 0. If the wall is at y is equal to 0, then we call this as tau 0. That is called the local shear stress. And then what is skin friction? I have already highlighted this, but I will again. So, the skin friction coefficient it is defined as a CF, and this is given by tau naught, that means the local shear stress, by half of 2 u naught square, and then we will define what is the drag per unit width. The drag, basically called the drag force per unit width on one side of the of a plate of length L. And it is defined as d is equal to 0 to L. You have already tau naught x dx. This is drag force per unit width on one side of a plate. Then we have what is called drag coefficient. And this is denoted by CD, and CD is nothing but it is d by half of rho u naught square by into L. This is called the drag coefficient. So, these are some of it. Then what we say that method of separation point. The point where the skin friction coefficient is the point where the skin friction coefficient is 0, that means CF is 0, and in other words that wall shear stress CF is 0. In other words, we can say the wall shear stress or local shear stress tau naught is 0. This is the point where CF is 0, or we can say tau naught is 0, and often this point is called a separation point. It can be seen that flow separation occurs in the region where pressure increases. So, flow separation occurs at a region where there is an increase in pressure near the boundary layer. Another point is that often the separation point is defined as the point where there is the transition between where the backward and forward flow take place. The transition boundary where forward and backward occur. And as usual, here you will have, because local shear stress will be 0. So, del v by del y is equal to 0 is 0, and in fact, it can be easily seen that it is independent of the separation point is independent of Reynolds number. Now, with this I will think of few more terms, that is what we call the displacement thickness. And displacement thickness, if I call it as a del 1, it is defined as 0 to infinity 1 minus u x y by u infinity x. This is the flow in the outer region of the boundary layer, and this is dy. And again what called the momentum thickness. And this is called del 2. This is equal to again 0 to infinity u by u infinity 1 minus u by infinity. Basically, u is a function of x y and this is a function of x, because this is the behavior of the flow at infinity large distance. and this is dy. Similarly, we have energy thickness. In fact, there are class of problems. Instead of going for direct U, many times we are interested in the calculation of this displacement thickness, momentum thickness, energy thickness, and that helps us in obtaining various physical quantity of interest, which will be obvious when we will work out one problem on this. And this will call 0 to infinity. This is called the energy thickness. This is again u by u infinity. U is a function of x y and 1 minus u square by u infinity square dy. This is called displacement thickness. So, these quantities are of in boundary layer flow theory, particularly when we solve by momentum integral method, then these quantities are plays a significant role. Then we have something called boundary layer thickness. And that is called del 99, that is boundary layer thickness. It is basically a difference, it is regarded at the distance between so it is regarded as that distance from the wall where the velocity on the boundary may differ from the potential flow velocity. It is that point that it is basically the distance from the wall where the velocity in the boundary differs from the potential flow solution. Potential flow velocity by 1%. In fact, this definition is quite it is not a very bit arbitrary, but it is one of the definition which is widely used, del 99, what we call the boundary layer thickness. Now, with this understanding of some of the basic terms, now we will go to analyze the boundary layer flow, boundary layer equation on a semi infinite flat plate. Basically, it is a 2-dimensional problem, and if I look at the governing equation, we have del u by del t in a 2-dimensional boundary layer equation plus u del u by del x plus v del u by del y, that is minus 1 by rho del p by del x plus nu del square u by del y square. This is plus we have the continued equation is del u by del x plus del v by del y is 0, and here by this minus 1 by rho, this term minus 1 by rho del p by del x is nothing but del u naught by del x del t plus u naught del u naught by del x. So, this is and u naught is the potential flow velocity. This is the potential flow velocity. The potential flow velocity. Then, with this, if this is the total, the 2-dimensional boundary layer equation. Now, what will happen? What will happen to the steady boundary layer flow equation? If the motion becomes steady, then we call this as the Blasius solution. What did Blasius did? 1908. So, basically it is the solution of the steady on provides the solution of the steady boundary layer equation. In a semi infinite flat plate. In a semi infinite flat plate with u is equal to u infinity at y tends to infinity, and this u infinity is constant, and this solution was called the Blasius solution. In fact, often it is called the first problem which was Pranthl's boundary layer equation. When it was derived, this was the first problem for which a solution was obtained, and in this case obviously del u by, because the motion is steady, we have del u by delta u is 0, and again since u naught is constant, then we have del p by del x is 0, and hence the boundary layer equation will be reduced to u del u by del x plus b del u by del y is equal to nu del square u by del y square and del u by del x plus del v by del y is 0, and here the boundary condition should be because that is y is equal to 0, at y is equal to 0, basically it is a flow. So, beyond this the flow is like this. So, now at y is equal to 0, u is equal to 0, v is equal to 0, and at y is equal to infinity, as y tends to infinity, that u is equal to u infinity. This is a constant flow, a streamline flow, u is equal to infinity. Sometimes we call this as the, beyond this is called the free stream, it is called the free stream velocity. Now, the solution of B, basically if I look at this one, I call this as B subject to C. To obtain the solution of B subject to C, what we will do? I say that here we will follow the similarity method, and in the similarity method what we will do? We will introduce the stream function psi. We will introduce the stream function psi, and in psi u when we were introduced such that u is equal to del psi by del y and v is equal to minus del psi by del x, and then if we set psi is equal to nu x u infinity root over into f of eta, where eta is equal to y times u infinity by nu x, and this is almost y by delta. Delta is the boundary layer thickness. In fact, when I have talked about similarity theory, I have said eta is some y by gx, and gx is proportional to the boundary layer thickness. In fact, it is follows this, and what I will do, I have brought in that a function f eta So, what I will do, I will by using this function f eta, the problem which is in two variables u v and the variables x y and y. So, we will recast the whole problem that is in b into a problem in f eta, that is one differential equation and it will come up. So, that will help us significantly to solve this problem. So, what we will do, if you will take u, and that is nothing but del psi by del y, u is del psi by del y, and then del psi by del psi we can call it as a del psi by del eta into del eta by del y, and this can be easily checked that this is nothing but u infinity f dash eta. In a similar manner, we will call v is minus del psi by del x, and it can be checked that this gives me 1 by 2 nu u infinity by x to the power half into eta f dash eta minus f of eta. Just follow the same procedure, one will get. In a similar manner, we will first obtain del u by del x, already del v by del y, del u by del y, del v by del y, and del square u by del y square. Just follow the same procedure of, if you do that and then substitute for ux, uy, vy, del square u in b, then in terms of f we will get only a single equation, that is f triple dash plus half f into f dash, that is equal to 0. This becomes the boundary layer equation reduces to this, and the boundary conditions that will be reduced to, and this is a nonlinear differential equation, ordinary differential equation, and which is known as the Blasius equation. So, as I have mentioned in the beginning that by using the self-similarity theory, we can always introduce a function, so that we will transform the boundary layer equation into just a single ordinary differential equation. However, this ordinary differential equation is highly nonlinear and it is not difficult, it is not possible to get a closed form solution. But what will happen to the boundary condition? The boundary condition will be f will be 0, f dash will be 0, at eta will be 0, and you can see that f dash eta will tend to 1 as eta tends to infinity. So, this will be the boundary condition, these are the boundary conditions. So, that we are solving this nonlinear differential equation subject to this, and then it is not always possible, as I have mentioned that it is this solution, closed form solution is impossible. It is not possible. So, what we will do, we will go for approximate solution, that means approximate solution by numerical methods. One has to, and in fact this solution was obtained by applying the shooting method, and the results, I will just plot the result how it is. So, my u by u infinity and u by u infinity, which is nothing but f dash eta, and the plot will be like this. If it is 0, 1, 2, 3, 4, 5, then f dash eta will be, if I call this point is 0 and this is 1, then my flow will be, this is of the nature of the flow, u by u infinity will behave like this. On the other hand, if I have another plot, that is, this is the longitudinal flow direction, longitudinal flow, and if I look at the transverse flow v by u infinity, then and my v will be v by u infinity into u infinity x by nu. This is the transverse flow direction. Then I will have eta on this side, this is eta, and then the flow direction will be this is also like this. So, this will be these results are obtained at the end of the day. So, you can say 0, 1, 2, 3, 4, 5. So, and in this case it is not possible. Once we get u and b, we can always get in a numerically, we can also get all shear stress, signification coefficient and other physical quantities of interest again numerically. So, this is one example, one of the famous example, which is known as the Blasius solution, which is obtained by the use of the similarity theory. Another example will work out on boundary layer equation, where the solutions of will apply the integral approach, integral method, and this problem will analyze to obtain the solution of integral method. What will do solution by the integral method? So, we will go for a plane incompressible boundary layer. So, solution of a plane incompressible boundary layer problem will obtain by this method. Let us consider a steady, consider again we will go for a steady motion, consider a steady 2-dimensional boundary layer equation or boundary layer flow, consider a steady 2-dimensional boundary layer flow. What we are doing here, I assume that, so I will have the basic equation will be del u by del t plus u del u by del x plus v del u by del y, which is equal to minus 1 by rho del p by del x plus nu del square u by del y square. See, then we have del u by del x plus del p by del y is 0. Since and this term is 0, since this term is 0, since I am telling I am looking at a steady problem, then what are the, and let me see, look at the class of problem, this what are the boundary conditions. I look at a problem where this is subject to the boundary condition, that as usual I look at infinite plate, the plate is infinity and here u is equal to so here y is equal to 0, u is equal to 0, v is equal to 0 and the y tends to infinity. I say u is equal to u naught x. So, it is not a constant like the previous example in case of Blasius solution. So, what we will do again, we have another thing, that is 1 by rho del p by del x, because this term this will satisfy minus u naught del u naught by del x, and this is plus, this is another, the pressure gradient satisfy this u naught, and since here it is again the motion is steady, so u is equal to u naught. So, in the process this satisfy p satisfy this equation. Now, to proceed further, what will it do? We will first integrate this equation, that means the boundary layer equation. If we integrate the boundary layer equation over the interval 0 to h, where h is a point, h is beyond the boundary layer, outside the boundary layer. So, I integrate over 0 to h the boundary layer equation, that is u del u by del x, because I have the steady, I have already taken del u by del t 0 plus v del u by del y minus u naught du naught by dx dy, and as I have told that h is a point, h is somewhere beyond the boundary layer, and this will give me the right side nu 0 to h del square u by del y square dy, and if I the right side what will happen, this will be if I integrate by parts, this will give a nu del u by del y, this is y is equal to 0 to h, and since h is beyond the boundary layer, h is beyond the boundary layer, so del u by del y will be 0. So, this will give me minus nu, because beyond boundary layer u is equal to u naught and h is somewhere. So, h is u naught x, it is a function of x. So, it will give you minus nu del u by del y, and that is at y is equal to 0, and that is nothing but minus tau naught by rho. This is called the local shear stress or wall shear stress, where tau naught is the local shear stress, or we call the wall shear stress. Further, as I have already mentioned that del u by del h, del u by del y at y is equal to h is 0, because it is beyond the boundary layer, and beyond the boundary layer u is equal to u naught x, and in the process that is 0. Now, if I look at the second equation, the second equation is del u by del x plus del v by del y is 0, and from this I will get my v minus del u by del x dy, and this is 0 to h. So, this is my v. Now, what I will do, I will substitute for this v, if this is a, I will substitute for b, particularly v here. If I substitute in a the value of b, then what will happen? If I substitute for b, then it will be y is equal to 0 to h, this will be del u by del y, u del u by del x, sorry, 0 to h, u del u by del x plus v is nothing but, so it will be minus 0 to h del u by del x dy into del u by del y minus u naught du naught by dx dy minus tau naught by rho. Now, let me analyze this term. This term is nothing but 0 to h, this is del u by del y into 0 to h del u by del x dy into dy, and this easily can be seen that this will give me u naught x 0 to h del u by del y just by integration by parts into dy minus y is equal to 0 to h u del u by del x. Now, I will substitute for this, this is my call it c, substitute for d for the second term from d in c, and if I do that, I will get it y is equal to 0 to h, that will give me 2 u del u by del x minus u naught du naught by dx minus u naught x into del u by del x. This will be what I will get. into dy. This will come here, u naught x del u by del y, del u by del x, this is u naught x, this is called del u by del x, sorry. Okay. So, u naught x del u by del x, this term is there, this is there, and u naught is there. So, this what I will get, and this is nothing but minus tau naught by rho. So, now this equation, if I introduce the, I can rewrite this is y is equal to 0 to h del by del x, this is u into u naught minus u dy plus du naught by dx into 0 to h u naught minus u dy and is equal to minus tau naught by rho, rather this is plus tau naught by rho. And this equation, if I now apply the definition of the displacement thickness, this equation will give me del by del x del 2 u naught square plus delta 1 u into d u naught by dx equal to tau naught by rho. In fact, the whole equation, and where I will say my del 1 u naught is 0 to infinity u naught minus u dy, and which is same as 0 to h u naught minus u dy. The reason is that because h is beyond the boundary layer. So, beyond h the contribution will be 0 because u will be u naught. So, that is why 0 to infinity u naught u is same as 0 to h u naught u. Similarly, del 2 u naught square is nothing but y is equal to 0 to infinity u into u naught minus u dy, and that is nothing but 0 to h u into u naught minus u dy. Same thing, these two definitions I have used. This is called the displacement thickness and this is called the momentum thickness. And this equation is called, this is equations E. This is called the momentum integral equation. This is called the momentum integral equation for plane incompressible boundary layer. Boundary layers. So, this is what I was telling, that finally we have brought it in a form of a differential equation in terms of a del 2 and a del 1, and if we will solve it and everything u is under the sign of integration here. So, once u is under the sign of integration, so we call this as an integral equation. Since momentum term is this momentum displacement is involved, we call this as a momentum integral equation. And we will in the next class we will see how the solution of this equation can be obtained, because initially I had to deal with a set of partial differential equation subject to certain boundary condition. Now, everything is converted to just one integral equation, what I was telling, the beauty of the integral method. And in the next class we will see how we will obtain the approximate solution of this integral equation. And in fact, this is one of the robust method to deal with the flow problems where flow singularity may occur, but it will adjust nicely. The solution will be, because here if there is some flow singularity here, this u or u square, because all these are integrable. If as I told that if there is a singularities are integrable, so these terms will take care of those things, and in the process we can easily get the solution. In the next class I will stop here, and in the next class we will talk about how we will get the solution of this in an approximate manner. This I will stop here. Thank you.